Hello. So carrying on from where we concluded in the last video, we we thought through, approved, and proved that cos alpha minus beta, right here, cos alpha minus beta equals cos alpha cos beta plus sine alpha sine beta. Now, to do this, I essentially just used law of cosines, which you can see up here for PQ squared. Compared the two results using distance formula also for PQ, and we got the final proof here of cos alpha minus beta. One could have also, just to clarify, one could have also focused on this triangle here instead and got the, like I said in the first video, the length of PT and TQ, which is really easy because we can glean that already. For example, TQ is going to be the same length of Rn, which is just cos beta minus alpha, so you have the length there. Then you could find the length of PT, which is just going to be sine alpha minus sine beta, and then you could use Pythagoras to find the PQ, the hypotenuse, which would just be PT squared plus TQ squared equals PQ squared, right? And you could work through all of that, and you're going to end up, essentially, rather than using distance formula, you're going to end up in the exact same place as this. So it's a little bit another of a minor variation on the proof, and like I said, there are many different ways to prove the angle sum identities. But now that it's been proven that cos alpha minus beta equals cos alpha cos beta plus sine alpha sine beta, we can look to quickly proving the other identities, angle sum identities, or compound angle identities. So to prove that cos alpha, let's just prove to start cos alpha plus beta. So let's just denote that as 1. Let's just denote this as 2. So cos alpha plus beta, we know equals cos alpha cos beta minus sine alpha sine beta. And so how do we prove this? Well, we've already proven cos alpha minus beta, as I said, so we can use this result to prove cos alpha plus beta very simply. And really all we're just doing is we're going to invoke not a cofunction identity, but a symmetry periodicity identity, that cos negative theta equals cos theta. And why is that the case? Well, that's because cos is an even function, right? And so what we can do then is take this result, this identity, and add negative beta. And what ends up happening is we get cos, I'll write it this way, cos alpha minus, we're substituting for beta, negative beta. So minus negative beta equals cos alpha cos beta plus, and sorry, I should have written that as negative beta, plus sine alpha sine negative beta. And what happens here is the double negative becomes positive, so we get cos alpha plus beta equals, and again, cos, we know here from this identity, it's a simple symmetry identity, cos negative theta equals cos theta, so this is just cos beta, so we write cos alpha cos beta. And negative beta, sine negative beta, maybe I'll write it over here, is again another symmetry periodicity identity, where sine negative theta equals negative sine theta, and that is because sine is, of course, an odd function, hence why we end up with cos alpha this becomes negative, that we can just pull that negative out front, and so we get negative sine alpha sine beta. And that is our identity, our second identity for cos alpha plus beta. So we've just proven cos alpha plus beta equals cos alpha cos beta minus sine alpha sine beta. Right, so next let's think about proving, on the basis of these results, let's think about proving sine alpha. Let's just start with sine alpha plus sine alpha plus beta equals sine alpha cos beta. Sine alpha cos beta plus cos alpha sine beta. So to prove this, it's a little bit more tricky. Whereas to prove, let's just sort of take a summary here. To prove prove initially cos alpha minus beta, that was our starting point. To prove cos alpha minus beta equals cos alpha cos beta plus sine alpha sine beta, we used law of cosines. We've used the distance formula, and also some basic first principle geometry, essentially, and also our knowledge of the unit circle, actually. So we've used a lot of different components or different concepts and tools to get that first result. Then to get our second result, we've used symmetry and periodicity identity, right? Cos negative theta equals cos theta. Likewise for sine, it's period or symmetry identity. Now, what we want to do, on the basis of all of these results, to find sine alpha plus beta, we're going to employ another trig identity. And that's what's cool about this proof, is we're using a number of different trig identities, and in some way it kind of just highlights their interconnection, I suppose. And this one's going to be a cofunction identity. And that is to say, we're going to essentially replace, replace cos alpha minus beta, so that's our starting point, was our initial result, and that's why I did a basic summary. We're going to start with cos alpha. I think this is how we're going to do it, at least. Cos alpha minus beta. Could be an error. I believe this is how we'll do it. So we'll go cos alpha minus beta, or sorry, cos alpha cos beta minus sine alpha sine beta. We've already proven that this is true, and we're going to take this result from the first identity, and we're going to add here, or replace, I should say. We're going to replace alpha with pi over 2 minus alpha. Hence, or therefore, what we get is cos pi over 2 cos, sorry, this should be plus, by the way, cos pi over 2 minus alpha, or sorry, pi over 2 minus alpha, and then we're going to double bracket this, actually, just to make it clear, more clear logically. And then we've still got our minus beta. Is that right? Cos pi over 2 minus alpha minus beta. We close our brackets. Yeah, I think that's right. And what we're going to do then for alpha is we're going to sub for both cos alpha and sine alpha. So that this then equals cos pi over 2 minus alpha, pi over 2 minus alpha times cos beta. And cos beta stays the same, and plus sine pi over 2 minus alpha sine beta. And from that point forward, we can do a little bit of algebra here. I think we can simplify it. Actually, we can just simplify it quite simply. We can just simplify here. we've got two negatives at this point, and so we can pull factor 1 out. What we end up with is cos pi over 2 minus alpha plus beta. Right, that's very simple. We just pulled out a negative sign that becomes positive, so now it's pi over 2 minus alpha plus beta. So that's we can most certainly do that, and that's it gets away with doing that, so that's fine. Just a little bit of manipulation. Now we're going to use the identity here. I think we have cos pi over 2 minus alpha. Well, the cofunction identity here is this equals, let's write it over here, maybe I'll even write the definition. Cofunction, one can look this up if you would like. It's a cofunction identity. Cos pi over 2 minus theta equals sine theta. That's one cofunction identity. Therefore, we can say this is cos pi over 2 minus alpha, right? Alpha is for theta. This equals sine of, in this case, sine alpha, right? Because so that's for theta. And we have another cofunction identity. Sine pi over 2 minus alpha equals cos alpha, or cos theta. Sorry, I'm confusing. I'm using alphas and thetas. So that's another general cofunction identity, and so therefore this right here, you can cross that out and say that's cos alpha. And where does this all leave us? Well, that's the big question, I suppose, because we still have this pi over 2 minus alpha plus beta here, right, on the left hand side, and we're going to need to simplify that a little bit. So how are we going to do that? So it's pi over 2 minus alpha plus, okay, well let me first just write this out. This is going to be equal, right? We have our cos beta, sine alpha. Actually, I'll write it this way, sorry. Sine alpha, cos beta. I was partly thinking of what to do with that. Sine alpha plus cos beta, we just have to work through it. And we've got our cos alpha now, and our sine beta. So we're getting somewhere. We've got exactly what we want. Here's the identity. Sine alpha plus beta is sine alpha cos beta. We've got that here clearly, sine alpha cos beta, plus we've got our correct sign, cos alpha sine beta, cos alpha sine beta. So we just have to simplify this, and I think I know how. And actually, it should be obvious at this point. Cos pi over 2 minus theta equals sine theta. And we need sine alpha plus beta, or in other words, sine theta, right? So this actually all just simplifies. This is theta. Alpha plus beta, we can just substitute for theta if we want. We can think about it that way. So what this all simplifies to is sine, maybe I'll make it more distinguished. All of this simplifies to sine alpha plus beta, which is our theta. And so therefore, maybe we just write it like this. Therefore, sine alpha plus beta equals sine alpha cos beta plus cos alpha sine beta. Yeah, so that's fun. This proves quite interesting actually when you think about it. We're using all of these different identities, and there are many other much more simple proofs, but fine, it's good to use all of these identities and just think about their connection, I suppose. We've got one more left, so we're almost done. Identity 4, right? I won't do tangents, the identities for 10 here in this video. I can do them separately if one wants. Maybe think about it geometrically would be fun. So this way we're just really relying on one algebra skills, and knowledge of identities, of various identities. Okay, so for the fourth identity, all we have left now is sine alpha. All we have left to prove is sine alpha minus beta equals sine alpha cos beta minus cos alpha sine beta. So this, how would one do this? Well, I think we're going to have to work off our other results up here, right above, where we got the sum identity. For the difference identity, we are going to use the symmetry and periodicity identity again. Would that work? Sine negative theta. Yeah, I think that's going to work just fine. Actually, yeah, negative beta. So what we're going to do is substitute negative beta for beta again, just like we did previously. So we get sine alpha minus negative beta, and that's going to equal sine alpha. We substituted for beta, remember, so this is a negative beta minus cos alpha sine, and again it's a negative beta. This is going to work fine. We're going to end up with a double negative, which becomes positive, and we are exactly where we want it to be. So that's a negative beta. I'm getting ahead of myself. The conclusion is nigh. So we've got a double negative here, right? So let's just simplify. This is sine alpha plus beta. So we've done something right, because that's where we want to be to prove our identity. Or actually, is it? Yeah, that's curious. In results, how would we do that? Yeah, right. Okay, that's the mistake I've made. I think I've made an error here. Actually, we want to use this result right here, like we did before, for the periodicity, symmetry, and density. So let's write it out. Sine alpha plus beta. We've already proven this. Sine alpha plus beta equals sine alpha cos beta plus cos alpha sine beta. Right? We want to substitute negative beta into here. We're substituting negative beta into this. So this is positive. What we end up with, let me erase this. What we end up with, therefore, is negative. Right? Now if we simplify, because this sine alpha plus beta, we substitute for beta, negative beta, we end up with sine alpha minus beta, and that's where we want to be, because we're proving this identity right here. And all of this is right. So what if we know cos negative beta is just cos beta, so we get sine alpha, and I'm hoping this works. This is just cos beta. We've already discussed why cos negative beta is cos beta, so that's fine. And now we have sine negative beta. Again, the symmetry identity, as highlighted, is that sine negative theta equals negative sine theta. This negative comes out. This equals negative sine beta. That negative comes out. We get double negative. It's positive. Therefore, cos alpha sine beta plus cos alpha sine beta, and oh, that's not right either. No, because this should have been positive. Sorry. We get this is negative, of course. Negative. We get this, right? Because the negative beta comes out. This is positive. It's sine alpha cos beta, cos alpha sine beta, and this negative cos beta is that's just cos beta. This becomes negative sine beta. I'll write it like this. That becomes negative sine beta. That negative sign comes out, positive, negative, so it becomes negative. The whole thing, right, so it becomes minus cos alpha sine beta, and that's the last identity, sum and difference identity. In the future, maybe I'll do some on tangent, and I'm going to actually maybe think about a few other different proofs, as they are quite fun. This one's cool, as we use all the various forms of identities, and yeah, so we've just proven the basic sum and angle identities, or compound angle, proof of compound angles.